Okay, welcome to this afternoon session where our first speaker is Pawel Hitczenko from Drexel University in Philadelphia, and he will talk about limiting distribution of some of the Graham, Knuth, Patashnik recurrences.
Okay. Thank you very much, and thanks to the organizers for this very nice meeting. And so I'll be talking about some of the Graham, Knuth, Patashnik recurrences. So those of you who know concrete mathematics know there are lots of problems in there that are classified from easy to research problems. And one of those is they propose this problem 89, which got upgraded to 94 in the second edition of the book. And what they called is for development of the comprehensive general theory of linear recurrences like that. You have a triangle of numbers, okay? They are indexed by n and then k that runs from 0 to n, and they form this recurrence like that. So n over k, this is n minus 1 over k times some linear function of n and k, plus n minus 1 over k minus 1 times another linear function of k and n, and the initial condition is you start at 1. Okay, so you have 6 real parameters: alpha, beta, gamma, alpha prime, beta, gamma, beta prime, gamma prime, and they wanted you to develop sort of theory how those recurrences behave depending on the parameters. So a number of people responded to that.
Just to check, this notation you're using, it's just, you could have said f of n.
Yes, it's taken from concrete mathematics. No, it's just as it's very notation. Some people use something different, but that's the notation in both editions, by the way. So, okay, all right. So here are some of the papers that were written since. The last two actually do not. So the first several, they do explicitly mention Graham, Knuth, Patashnik in recurrences. The last two actually don't. So although they oppose the book, so but they sort of analyze aspects that Graham, Patashnik would be interested in. And as I said, the interest is in doing in some sort of generality. So if you consider specific values of the parameters alpha, beta, gamma, alpha prime, beta, gamma, gamma prime, you get specific triangle of numbers that about most of them we know everything. So for example, if gamma is equal gamma prime 1 and the rest are 0, you get standard binomial coefficients. Okay, so here are some of the things that have been done. So three Spaniards, Barbero, Salas, Villaseñor, so they actually looked at the bivariate generating functions of those triangles, and they, in a sense, derived explicit formula, except that four formulas are not really, well, for my standards and ability, workable. They are given in terms of a function whose inverse is given as a series that is not really very convenient to work with. Then there is a fairly long paper by Mayer who analyzed relationships between those various recurrences, the transformations on some into others and things like that. And then there were a series of papers. So Wilf was one of those who first. So for example, here's a explicit result. So if alpha prime is 0, then you can actually get an explicit formula for the solution, which Herb Wilf derived. And so he noted two things that were interesting. So first of all, you have three, in his view, most basic triangles of numbers present in one formula. But secondly, you have, this is a polynomial in those 5 parameters that factors as 2 polynomials. One of them is in prime parameters. Okay, remember alpha prime is 0, and the other one is non-prime parameters. So he thought this was sort of curious, but I don't think he pursued it any further. So anyway, that's so, and as I said, more results along those lines. So these are a thing called factorization. So you want to factor those recurrences into sort of simpler things. So more results along those lines were obtained by Rege, Freukmann, and also Stivey. And in another direction, what Herb Wilf showed that if beta prime is 0, and you look at the row polynomials, so you fix n, and you run generating polynomial for k, so in this case, you get a sequence of polynomials of increasing degree. So he showed that when beta prime is 0, all those polynomials have real roots. Okay, and he also showed that if b prime is non-zero, then in general you don't have it. Okay, so that's that. So what I will be interested in is sort of limiting distribution about solutions of those recurrences. So this wasn't addressed in any of those papers that I cited. So let me remind you, so if you have this row generating polynomial, if you normalize it by value at 1, then you can think of the resulting thing as a generating function of the integer valued random variable whose probability that, so this is integer valued, probability that it's equal to k is this coefficient n over k normalized by the whole sum. Okay, and what you want to know is what's the limiting distribution as n goes to infinity. Okay, so that's what I'll do. And so with that recurrence, the generating polynomials satisfy this two-step recurrence. So Pn is, again, linear function in x with coefficients depending on n possibly times the previous polynomial plus a fixed polynomial, quadratic polynomial in x times derivative of the previous polynomial. And let me say that this is sort of special case of the two-step recurrence that, so people were considering recurrences like that Pn is some function of x times Pn minus 1 plus another function of x times Pn minus 1 prime. In particular, H.K. Huang, from whom we heard just a few minutes ago, relatively recently with two other people from Academia Sinica at Taipei, they wrote a very, very long paper that they were interested in what they called a generalized Eulerian recurrences. So their functions ANX, BNX were of that form. So AN was a fixed polynomial in x times n plus another polynomial in x, and Bn was independent of n, as it always happened, and it was a polynomial times a factor 1 minus x. And there were additional conditions. So, for example, the value of alpha at 1 had to be strictly positive, and I think also the value of alpha 1 plus gamma at 1 had to be strictly positive, things like this. So strictly positive, you do have this n present here. Okay, and then, as I said, the paper is over 120 pages long. They run, online encyclopedia of integer sequences, identifying over 600 examples that fall into this. So it's very comprehensive paper on that aspect. So there is, but what I want to maybe I'll come back. So it was very crucial that Bn of x vanishes at 1. Okay, so one of the main methods they developed was the method of moments. So they proved convergence in distribution by proving convergence in moments. So as we know, the Arf moment is related to Arf derivative of that polynomial. But if you try to set up a recurrence for the Arf derivative of the polynomial, then you have R plus 1 derivative. And that causes a problem unless after evaluating at 1, this thing disappears. And this is exactly what has happened. Okay, so that's why this thing was important. Okay, so all right, so there is an overlap with what they've done, but there are also things outside. So as I said, the title has some of the Graham Knuth Patashnik recurrences. I can only do the situation that alpha prime is 0 and the remaining 5 parameters are non-negative. Okay, this admittedly doesn't cover a lot of recurrences that might be of interest, but also covers a lot of them. Okay. So let me first say what happens. So first of all, if beta prime is strictly positive, so from now on, alpha prime is 0, the remaining 5 parameters are non-negatives. Okay, so there will be various cases depending which of them are 0 and which of them are strictly positive. Okay, so the first thing is when beta prime is positive and at least one of alpha and beta is positive. Okay, when you have that situation, then you get that. First of all, mean is linear in n, and you have coefficient that you identify from those, and the variance is also linear in n with another coefficient. And when you normalize in a usual way, so you subtract of asymptotic mean and divide by asymptotic standard deviation, you had standard normal random variables. Okay, so one of the expression here is rho. The formula for the rho is here. So this works. So yeah. So in particular, if only one of the remaining alpha beta is positive and the other one is zero, this behaves very nicely. You could either repeat the same argument that is used for when both are positive, or you can just take the limit as those, the parameter that is zero. You take the limit of that parameter goes to zero, and everything is preserved, including those expressions for the variance and the mean. Okay, so this is now what happens when both of them are zero, when beta is positive but alpha and beta are zero, then this breaks down. You do not longer have a Gaussian limit. You have a very, I thought, weird limit. So first of all, let me remind you, so this is a probability distribution function of a negative binomial distribution with parameter R and P. It was mentioned, I think, yesterday. When R is a positive integer, then this is, I guess, when R is a positive integer, this is usually interpreted as a number of failures before the R trial, but actually R doesn't have to be an integer. It's just enough that it's a positive number. This is legitimate distribution. So in that case, so as I said, when beta is positive and alpha beta is zero, the xn has exact distribution, exact distribution that is actually negative binomial with those two parameters, okay? Conditioned on its sum with independent Poisson with that parameters being equal to 1, to n. Okay, so this is very, I thought this was a weird distribution. So you are, so neither parameters of neither of those two depend on n. So they are constant in n, and you are, so as n goes to infinity, you are conditioning on the sum of those two being n. So this is diminishing event of diminishing probability. Okay, and then it takes, from that, it takes, you know, a little bit elementary asymptotics to get the mean is like n minus a constant, and variance is the same constant asymptotically, which again, after that is not surprising. Okay, all right, and so this is when gamma is positive, and when gamma is zero, then xn degenerates to almost surely equal to n random variable. Okay, so this is the description when beta is positive. When beta is zero, then again, you have two things. Well, if beta prime, I'm sorry, when beta prime is zero, and in addition, if beta is zero, then again, if gamma prime is positive, you have still asymptotic normality, except that the both mean and the variance are of logarithmic order. Okay, and then when alpha is zero, in addition to that, then your xn is just binomial distribution with parameters n and this probability, so you know it's exactly. And then when gamma prime is equal to zero, then again xn is degenerate. So what I should say maybe in this case, when both beta and beta prime are zero, remember the recurrence was that the nth polynomial was something on the n minus first polynomial plus something times derivative of the n minus first polynomial. If both beta and beta prime are zero, this something in front of derivative of Pn minus 1 is identically zero. So that means your recurrence is Pn is something times Pn minus 1. Okay, so that means that Pn is a product of linear factors. Okay, so what that means, if you normalize it, that the probability generating function is just probability generating function of some of the independent indicators. Okay, once you know the probabilities of those indicators, of course you know, so you know what is the distribution. Okay, so here what is, and this is regardless whether alpha prime is zero or not. Okay, so basically when as long as beta and beta prime is zero, you don't have the second factor. You have sum of independent indicators, and probability that k of them is equal to 1 is this thing. So in particular, if alpha prime is equal to gamma prime is equal to 0, this probability is 0, so have identically zero random variable. Okay, so all right, but I guess the reason I stated in this way that from the you have sort of uniform approach to the proof. Okay, you don't have to sort of consider various situations. All right, and then finally, beta prime is 0. This time beta is positive. So previously beta was as well 0. So when beta is positive, then in the independent work that was published last year, you get asymptotic normality with mean that is of order n over log n, and the variance that is of order n over squared of log n. So this is like the Stirling numbers of the second kind. Okay, the number of blocks in a set partition of an element set that follows this type of thing. Okay, and then finally, if alpha is positive as well, then what you have again, you have asymptotic normality, but both mean and the variance are sublinear in n. Okay, so as I said, these are all positive. These are non-negative positive numbers. So this is number less than 1 and positive. So they're all right. So that's the full description of what is happening in those circumstances. Maybe I'll say a few words about the approach and the proof. So it's very much analytic combinatorics. So you write bivariate generating function, okay, and then if you want that, if you extract the nth coefficient of fzx divided by normalized by zn coefficient of fz1, then this is a probability generating function of the underlying random variable. So if you can asymptotically approximate those coefficients, you get approximately what's the probability generating function, and then you get the limit. Okay, so that's basically what is happening. So we had, I showed you, we had this recurrence for those row polynomials Pn. When you write the bivariate generating function, then it's straightforward that this generating function satisfies the partial differential equation, which is like this. So derivative with respect to z times this function 1 minus alpha z minus alpha prime xz minus this polynomial times derivative, partial derivative with respect to x is equal to a function times your bivariate generating function f. Okay, and the initial condition is that f of 0x is equal to 1. Okay, so all right, so it turns out that under the assumption that alpha prime is 0, this partial differential equation can actually be solved by what is called the method of characteristic. Okay, so the method of and I think it was Wilf was the first one in his paper in 2004 that he actually noted. I mean, he used Maple to do it, but Maple will do it for you. Even in 2004, it did it for you. Okay, so yeah, so that's one way of approaching. And then you have at that point you have explicit form of the bivariate generating function, and then you can use tools from analytic combinatorics. So that's what I did. So so this is your once again, this is your bivariate generating function, and then you open Flageolet-Sedgwick, and sooner or later you will find a theorem that applies. So in this case, this function is subject to what they called algebraic singularity scheme, and this is the theorem that allows you to conclude under certain circumstances that you have a normal law. And so let me tell you what happens. So this theorem, this algebraic singularity schema, as presented in the book, have three assumptions. One is what they called analytic perturbation, which tells you that your bivariate generating function has to be of the specific form. The second condition is that certain quantity should not vanish. That's what they call variability condition. And then there is a third condition that tells you that another quantity should not vanish, and they call it a non-degeneracy condition. Okay, and what is happening here, if both alpha and beta are 0, then this variability condition fails. And if beta prime, when beta prime is positive and both alpha and beta are 0, then this variability condition fails. And when beta prime is 0, then this non-degeneracy condition fails. Okay, so in those cases you cannot do it. Okay, and as I said, and they have it what they call perturbation scheme, as I guess I was attending Steve's seminar a few weeks ago in Philadelphia, and I guess in modern language you would use analytic combinatorics and several variables to get more modern statement of the things. But anyway, this is so. Okay, so now what happens? So as I said, if beta is 0, then you cannot use this algebraic singularity scheme, but there is what they call variable exponent perturbation, and in that case, as they say in the book, you should expect normal law with the logarithmic size of the mean and the variance, and this is what is happening. And then finally, when both when beta is positive and this is 0, then your f is actually analytic, and you can use saddle point method to crank out the asymptotic normality. And when both of them are positive, then your function is of that form, which something similar appeared, I think, today. Okay, so basically it has, I mean, it has exponential singularity here and sort of the same singularity, similar singularity here. So it goes back to Wright, who developed method based on the saddle point to get asymptotic coefficients like that. Flageolet and Sedgwick briefly mention it. Okay, so all right, so maybe okay, let me go back. Not yet. So one thing that when one case of this negative binomial random variable added to independent Poisson, basically what happens is you cannot use any of those things. But if you look at if you expand by just brute force into power series and you look at the coefficients in front of Zn, then you can actually, after some work, you can identify that this is exactly what it is. This is a probability of negative binomial added to independent Poisson and conditioned on the sum being n. So this you just read off from the form of generating function. So I have few comments. So as I said, all of this rests on the fact that you do get explicit form of a bivariate generating function, which when alpha prime is not equal to 0, then generally is not true. There is one exception when alpha prime is not equal to 0 and both alpha and beta are 0. Maple, or you can do it by characteristics, I guess by hand. They still gave you explicit form of the bivariate generating function. Here it is. And then if you isolate this first term and the rest and normalize by 1, then you have this factor, and then you have the rest. And this factor you can identify if this is probability generating function of a negative of a Poisson random variable with parameter gamma over beta prime. The rest turns out to be degenerate. So basically, in this case, you get that it's actually, the other one is asymptotic. So basically, in that case, your xn is asymptotic to n minus Poisson random variable. Okay, so that's the story. To close, as you might guess, I've been reading Flageolet Sedgwick a bit over the last time. So one of the things that when they talked about using ordinary differential equation in analytic combinatorics. So what I found is the statement that by contrast to ODEs, partial differential equations have so far been only scarcely used in analytic combinatorics, okay? And I think, you have many more instances that it's very natural to expect that your bivariate generating function or multivariate generating function will satisfy some sort of PDE. So maybe it's time that sort of PDEs, by the way, this is not, I'm probability as you can, okay? So this should be E, okay? So maybe it would be worthwhile to look at, general properties of PDEs versus analytic combinatorics, okay? So I think I'll stop here. So thank you very much.